Today we begin the discussion of limits, and we'll mention briefly limit laws, which are just common sense rules for limits. All right, let's consider the function f of x equals x squared minus 1 over x minus 1, rational function. Two questions. How does that function behave at x equals 1? How does that function behave near x equals 1? Two different questions with two radically different answers. At x equals 1, that function is not defined. 1 is not in the domain of that function. The domain of that function, negative infinity to 1, not including the 1, 1 to infinity. It just doesn't exist. But near x equals 1, near x equals 1, like as we get to 1.05, 1.04, 1.01, 1.001, or from the other side, 0.99, 0.999, etc. Near x equals 1, we could run a bunch of numbers with x getting closer and closer to 1, and we would see a pattern emerge. But it's not necessary to do that, because if x is near but not equal to x equals 1, then we can rewrite this as x plus 1 divided by x minus 1, factoring that numerator, divided by x minus 1. As long as x does not equal 1, this is not 0, we can cancel. And what happens is that this rational function, for any value of x other than 1, behaves exactly like the line y equals x plus 1. So as x gets very, very close to 1, as x approaches 1, x plus 1 approaches 1 plus 1. Now, that does not mean that this function will ever equal 2. It will not. But in the language of limits, we say that the limit of the function x squared minus 1 over x minus 1 as x approaches 1 is 2. Because, again, as x approaches 1, not just this, but this approaches 2. And in fact, since we have that cancellation, if we were to graph this rational function, the graph would be identical to the graph of y equals x plus 1, except at the point 1, 2, there would be a hole in it. So the graph would look just like that line, with the exception of that hole. But from either side, as x gets closer and closer to 1, y would get closer and closer to 2. Now, a limit of a function then, if we're to define it, is a value that function, the value of y, that the function approaches more and more closely as x approaches some stated value. Here the stated value is 1. So again, the limit of that function as x approaches 1 is 2. Meaning as x approaches 1, y approaches 2. It doesn't matter whether y can ever equal 2. Well, because let's do this. What is the limit of the simple function x plus 1 as x approaches 1? Well, that is also 2. In that particular case, the function also happens to equal 2. But it doesn't matter whether it does or not. As long as we approach the 2 more and more closely as x approaches 1, that's the limit. Okay, now, whenever you're presented with a limit, and we'll write a generic whenever you're presented with a limit, we'll just say the limit as x approaches c of f of x, the first thing that you should always try is direct substitution. In other words, try to get f of c. If you get a real number, a finite number, or if it's going to infinity or negative infinity, if that's clear, then you're done. But, again, let's go look at what we had here. we have, if we plugged in the 1, 0 over 0. As we shall see later in our study of L'Hopital's rule, this is called an indeterminate form. Zero over zero, plus or minus infinity over plus or minus infinity. An indeterminate form. Why? Because you cannot determine anything from that. You have no idea what the limit is if direct substitution yields 0 over 0. Okay? So, when that happens, you have to find a way to eliminate that 0 over 0. Now, again, later on we'll do L'Hopital's rule. But for right now, we can do that for certain functions as we did here. We used the algebraic manipulation of factoring and canceling, and that eliminated the indeterminate form. Okay? But again, the first thing you always try is direct substitution. In fact, if I had this, the limit as x approaches 2, no problem. If I plug 2 in there, I get 4 minus 1 is 3, over 1 is 3, and I'm done. In fact, for any value of x other than 1, for any value of x in the domain of this function, direct substitution will work. The limit of a rational function, and we can remember this, the limit of a rational function for any value of x in the domain is simply the value of the rational function. For a polynomial, it's even easier. If you've got a polynomial, we'll call it p of x. Well, the limit of p of x as x approaches c is always just p of c. Because there are no discontinuities. It is always a smooth curve, so very easy. Polynomial functions. Okay, but you always try direct substitution first. Now, we just saw one method whereby we can evaluate a limit when we have an indeterminate form, and that was factoring and canceling. But we can't use that for every type of function because sometimes that's just not possible. So if we take a limit like this, the limit as x approaches 2 of the square root of x squared plus 5 minus 3 over x minus 2. Okay, if you plug in 2 there, you get the square root of 9, which is 3 minus 3 over 2 minus 2. You get 0 over 0. Clearly, there's nothing there we can factor. But we do have an algebraic technique for evaluating this limit. And that is multiplication by the conjugate. Okay, you may remember, I hope you'll remember, that a plus b times a minus b equals a squared minus b squared. Factorization, the difference of squares, is the product of two conjugates. A plus b and a minus b are conjugates of each other. And if either a or b or both is a square root, when you multiply them together, both get squared, the square root disappears. That tells us how to deal with this kind of limit. We multiply numerator and denominator, and we have to do both because we're multiplying by 1. We do not want to change the value by the conjugate of this numerator that contains the radical. So the conjugate would be, if this is a minus b, the conjugate would be a plus b. When we do that, we get the limit as x approaches 2 of a squared minus b squared. Now clearly x squared plus 5 minus 9 is x squared minus 4. And that would be divided by x minus 2 times the square root of x squared plus 5 plus 3. All right, one more step. X squared minus 4, again, it's a difference of squares. X squared minus 4 factors. 2 x minus 2 times x plus 2. As x approaches 2, but not equal to, we're left with that. Now, at this point, we have now eliminated the indeterminate form. We can directly substitute the 2 in there, and we will get 4 over 6, and our limit is 2/3. Okay, so we've seen two algebraic manipulations now for eliminating an indeterminate form. Factoring and canceling, when that can be done. Multiplication by a conjugate, when that can be done. And of course, factoring and canceling ended up being part of that. Okay, one more. And that one more is used when we get something like this. The limit as x approaches 3 of, let's say, 1 over x minus 1 over 3 divided by 3 minus x. Okay, if we plug in 3, direct substitution, we always try first. 1/3 minus 1/3 is 0. 3 minus 3 is 0. We got 0 over 0, another indeterminate. No factoring to be done there. No conjugate. But in this case, where we have complex fraction, let us multiply by the common denominator on those two fractions. Multiply numerator and denominator. That will do a neat thing for us called clearing the fractions. 3x times 1 over x is 3. 3x times 1 over 3 is x. Divided by 3 minus x times 3x, 1. As x approaches 3, this approaches 1/9. Factoring and canceling, multiplication by a conjugate, multiplication by the common denominator. 3 algebraic manipulations. Now, sometimes a limit just doesn't exist. We have to accept that. We'll just look at a couple of examples right now. Let's take the limit as x approaches 0 of the absolute value of x over x. If we were to draw the graph of that function, when x is positive, the absolute value of x equals x. And so, for positive values of x, we've got 1. When x is negative, the absolute value of x equals the negative of x. And we've got y equals -1. At 0, there is a jump. And it's called a jump discontinuity. At 0, the limit just does not exist. Okay. One other, if we were to take the limit of 1 over x as x approaches 0. This is a function that comes up so often. Please get yourself familiar with it, okay? As x approaches 0 from the right, we have 1 divided by an infinitesimally small positive number. That's going to infinity. As x approaches 0 from the left, we have 1 divided by an infinitesimally small negative number. That's going to negative infinity. The limit of 1 over x as x approaches 0 does not exist. Now we can talk about one-sided limits, which we will do in a later lesson, but suffice it to say that the ordinary limit here for both of these does not exist. Okay. The limit laws, just briefly, very briefly, because they're just common sense. Okay, suppose you have two functions, and we'll call them f of x and g of x, and we say that the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is M. Well, the limit as x approaches c of f of x plus g of x, if you were to take a wild guess, you would probably say L plus M, and you'd be correct. Let's get that out of there. And if this is minus, it would be L minus M. The limit as x approaches c of some constant times f of x would be that constant k times L. And that's the way products and quotients, the same thing. All right? The limit laws are just common sense laws, and that's it for now.